them finished today are section 6.1 on arc length. And we've done a lot of questions on finding arc length in areas or sectors, and I want to do just another one of them. We've done some applications. I want to do a few more of those, and we've got this little thing I haven't mentioned called angular speed, which isn't that hard, but we'll do something using that. So here is my arc length and area sector question, right? So let's imagine that we told you that the arc length is 10 meters and that the radius was 5 meters. And then I asked you this question: find the area of that sector. So what on earth are we going to do? Because the information they've given me was basically from here, but the thing that I need to find is that guy, right? The area. So tell me you don't need to do the details of the numbers, but exactly how are we going to do that? What are we going to find first, and so on?
Theta and dividing the arc length by the radius.
Looks like a good start. So the arc length is r times theta. 10 is 5 times theta. You know, I've made the question nice and easy for me. Theta is 2 and 2 radians, right? We all understand that the angle's radians unless they tell you otherwise, right? So the angle is 2 radians. So now I can get the area of the sector. And it is just a half r squared theta. The circle hasn't changed. It still has a radius of 5. And theta is 2. And you can see I made my life nice and easy again. And the answer is, I believe, 25. And since the units were meters and it's an area, it's 25 square meters. So are you comfortable about finding missing angles, radius, or arc length, finding missing angle, radius, or area of sectors in arcs, right? I think we've done every permutation you could possibly have. This was kind of the last permutation where the thing was in sectors, but the answer was going to be using area, right? So it was kind of a transition between the two. Of course, you could do it the other way around. Couldn't I tell you what the area was and then eventually ask you to get an arc length, right? You could, it could go that way. Right. We good? Right. So let's move on to some of the application ones. We've done a few of those. There's one more that piqued my interest, and this one is question 16. And then after that, we're going to do a really big one, which I think is my favorite one in this whole section. So in this question here, we're being asked how many revolutions? So how many times does a wheel need to turn? Does it take? With a car, I think I did this one, or one at least similar to it, that has a diameter of 16 inches. Did we do a question, how many revolutions? I know we did some with a car wheel, but was it this one?
We weren't looking for revolutions, we were looking for how many miles per hour.
Ah, okay, so this is a little different. Oh, so how many revolutions does it take with a car that has a diameter of 16 inches to travel 1 mile? Okay, so we'll start off with our wheel. And is it okay for me to say the radius is 8? And it's pretty obvious why. Great. Diameter is 16, the radius is 8. One revolution is basically that guy, right? In this case, then, one revolution is 2 pi times 8. So far, so good. And I could turn that into a decimal. I'll leave it right now. So if you want to find how many revolutions it takes in a mile, don't you have to take 1 mile and divide it by that number there, which is what, 16 pi. Now, this is in inches. Don't I have to turn miles into inches again? What is the magic number? How many feet in a mile?
528.
I've already got that mump over with, so I don't need to do it again. So isn't there 12 times 5,280 inches in a mile? So that is 1 mile in inches. That is 1 circumference of a wheel, 1 turning of a wheel in inches. And then time for calculator. Bracket 12 times 5,280 divided by 16 pi. And you know I put brackets around everything just to be safe. And the answer that we get is, well, as a decimal, it looks like that. But they want the answer to the nearest whole number. So there you go. In a mile, your wheel would turn 1,261 times, which is quite a lot. You can imagine that that would be a lot of turns. Are we okay with that question? How many revolutions? Now, the question I was talking about was one of my favorites, if not my favorite from this section, is this question here, which is question number 19. So they give you basically a picture. See if I can find it. Yeah, this is what the picture looks like. I've just rewritten it in a slightly different form. Right. Looks like this guy here. You see it? Make it a little bit bigger. And there's a cow, and it's attached to a tether, you know, like maybe a dog was on a leash kind of thing. And this cow is going to eat all this light green grass. And our problem is to find out what that area of that grass is. And they tell you how big A is and B is and C and D and E. So that distance is A, this distance is B. That's how much the longest line is C, then D and E. So when you write all of that information onto the diagram, which I think is helpful, you've got that. Now we need to find the total area that that cow would be in. So you imagine the cow, it would eat grass like this. Now, what in fact is going to happen here is that there's really 3 things that we need to find. Is it? No, there are actually 4 things, I should say, that we need to find the area of. I want you to imagine the big one would look something like this. And that would be 100. So I'm going to call this one, I don't know, I'll call it number 1. Number 1 is that bit. You agree that's the biggest chunk, you know, that the cow could get. So what do I know? I know the radius is 100. And wouldn't you say that the angle here was 90 degrees? Great. Now 90 degrees in radians is pi upon 2. Are you comfortable with the theta being pi upon 2 and why it's that number? So number 1, right? What's the area of it? It's 1/2 radius squared times theta. 1/2 times a radius 100. I know it's 100 because right, that distance 100, and we'll assume that the cow keeps it nice and tight as it eats and munches its way. So that's 100 squared times pi upon 2. And I'll go to my calculator, I think, for this one. Oh God, I see, that's difficult. Oh, wait a minute, that's a quarter. So I'll go 100 squared, which is that number. I'll divide it by 4, and I get, I'll just leave it as a multiply pi. A half times 100 squared, and that guy gets you 2500 pi. That's good. Now, changing color. When the cow gets to here, right, there's a change, right? It goes down like that. So what you're going to get here, you might think is the whole quarter, but it's not. It's not going to be quarter of a circle, radius 50. It looks the way I've drawn it, it should be. Here's my argument. Do you see this entire line from here to here? Isn't this bit here 40? Now, can you see why this bit here is 40? Right? The total length is 100. So when the cow gets to here, won't it be 60 plus another 40 more? So when the cow starts eating, won't the cow do that guy? In other words, this little piece here is number 2. So let's see what that looks like. The radius is only 40 now. 60 plus 100, right? 40. The angle is quarter of a circle. And so the area of 2 is 1/2 radius squared theta, 1/2 times 40 squared times theta. And I'll go to my calculator and see what that is. You do 40 and you square it, you get that, divided by 4, you get 400 pi. Okay, so that bit's done, that bit's done. Okay, now let's look at this top piece. When the cow gets to here, that total length will be 100. If this bit is 50, won't that bit be 50? And so when it eats inwards, aren't you going to get a quarter of a circle whose radius is 50? Does that make sense that this piece here, when I show you colors to shade things, won't this piece be a quarter of a circle, but the radius is 50? You see, you have to go hunting for the radius. It changes as, you know, the thing progresses. So in this case, the radius is 50. It's still quarter, which is that guy. So the third one, which is what I'm going to call that piece, is 1/2 r squared theta, 1/2 50 squared times pi on 2. Go back to calculator. 50 squared divided by that guy, 625 pi. So I know this one, I know this one, I know this one. You might think you're finished, but there's a little piece down here. Right. One more piece. That little piece in there, I'm going to call number 4. I need to know its radius. I can tell it's quarter of a circle, but I need to know its radius. What is it?
40.
I didn't quite catch what you said. Might be right, I just didn't hear it.
40.
I agreed, 40. You want to tell people why it's 40? You're right. Where did you get it from?
The radius of sector 3 is 50. And
Agreed.
then, you know, the distance A is 10, so 50 minus 10.
Does that make sense, guys, where that 40 came from? Now, if you know the radius, which we do, and you know the angle, which is quarter circle, then number 4 will have an area of 1/2 r squared theta, 1/2 40 squared times 1/2, which I think I got from an earlier question. So that's also 400 pi. It's a cool question. I mean, there's lots of bits to it and you have to think about it. So what do I know? I know it's that bit, plus that bit, plus that bit, plus that bit. You agree? And so if I add all those numbers up, and forget about the pi for a minute, I've got 400 plus 2500 plus another 400 plus 625. I get a total area of 3925 pi, which if I turn into a decimal is 12,331 to the nearest whole number. So that cow has got 12,331 square feet of munching to do, which is plenty. Now the problem, well, not problem. You might think, oh, well, I don't need to do this question because he's done it for me. WebAssign changes all these numbers. So you're going to have to do it with maybe 150. And that's 30, and that's 70, and this is 50, you know, whatever, right? So your question is going to be the same process, but these numbers will be different unless by a sheer fluke you got exactly the same ones I got.
I myself had it at 120, and I did it yesterday.
So the one you got was slightly different numbers, but the same idea, right?
Yes.
Yeah. Work out okay? Did you get it right?
Yeah, eventually. And then I realized I probably should have just waited until you explained it.
Okay. Did you try it once you figured it out? Did it end up being similar to the way I did it, or did you figure out a different way of doing it?
No, this is the way that I ended up doing it.
Yeah. Okay. I'm taking a
I
guess
have a
here.
question.
Yes.
How come it's only 3,925 pi? How come it's only one singular pi versus, because every single one has a pi unit in it?
Yeah. So if you
Yeah,
add,
well,
it's like adding x's. So it's like 400x plus 2500x gets you 2900x. When you add things together, you're just collecting multiples of pi. So you just need to add the 400, that number, and that number, which I hope
Okay,
is
then-
3925. Right. So, since you're adding things together, not multiplying, you just get pi.
I have a question too.
Go for it.
Is a quarter of a circle always just going to be pi over 2?
Yes.
Okay.
So let's prove it to you.
I have a
Just
question as
once.
well
Right. Hold that thought.
after that.
Right. Here is 90 degrees, right? Quarter circle. And the angle in radians is pi upon 2, right?
Yeah.
Now you can do it two different ways. The first way, you could simply just say something like this. A complete circle is 2 pi.
Yeah.
And so a quarter of a circle
Which
is
is
half a pi.
okay.
And maybe I don't need the other way, because if that makes sense, why show you another way of doing the same thing, right?
No, that makes sense. So if going back to the problem, you think you wrote pi over 4 for
I
the last
didn't,
one?
did I?
Okay.
Oh, did I?
Yeah, I think it was like pi over 4.
Oh, the good news is that I used 2,
Okay.
so it was okay. So the number
that
is
threw
right.
me off.
Yeah.
Okay,
Yeah,
thank you.
that just, yeah, they're all the same. They're all quarters.
Pi over 2. Okay, cool.
Pi over 2. I think you had a question, Katie.
Oh yeah, because I thought that like it was pi over 4, like it was different from
Oh
you.
no,
So,
it's
like,
just
the
me
math was
making a
wrong?
mistake.
Yeah, okay.
Right,
I was
right.
like, that's not right.
Well, that'll give me a good teaching moment. You may by now have realized that regardless of what I say, I am not perfect, and that I do make mistakes. And I really like it when you point them out, because it helps everyone, including yourself. So I don't want you to do, if I write down, as I probably will in the next 8 or so weeks, that 2 times 3 is 5, you are not going to say, well, he's got 2 degrees and he's been teaching for 42 years. So if he says 2 times 3 is 5, it's just some funny algebra I've never seen in my life before, but it's 5. And I'm not going to argue about it because he can't possibly be wrong. No, 2 times 3 is 6, and I am wrong. End of story. But you will tell me that I am wrong in case someone, not Caitlin, because she definitely didn't feel it was correct. You will tell me. And most of the time, I will have made the mistake and I will fix it. And sometimes I didn't make a mistake and you just falsely thought I had. And I don't have any problems with that. And so don't feel, oh, I'm frightened to point that out in case it's not wrong anyway, you know, and somehow I'm going to look foolish. You're not going to look foolish. You know the number of mistakes I'm going to make in a day is going to beat any number of mistakes you're going to make, right? So yours doesn't even count if you, and you know, if it's right, that's happy. I'm saying, no, I was right, and we move on, and no big deal. Or more likely, oh, you're right, that should have been pi upon 2. And don't know if you liked that one, but I did. That was a real cool puzzle. I like ones that you have to do stuff to. I'm going to just check that off now because we've kind of done them. And we've got this thing called angular speed. So I'll show you an example of the question and kind of take you through how you're going to calculate it. So what we've got here is a ceiling fan. That's a ceiling fan. Can you see it? Rotating ceiling fan. I'm an atrocious artist, aren't I? Okay, let's try better. Does that look more like a ceiling fan or should I have not bothered? Probably shouldn't have bothered, okay. But anyway, it's rotating as ceiling fans do. And they tell you that each blade is 28 inches. So basically they're telling me that, you know, if you draw vertically, can imagine that's the blade, and you know there's more than one of them, but you know as it rotates, right, the radius is 28. That's good. And then you're told that the blade does 55 RPM, which is short for 55 revolutions per minute. And we are being asked to find what is called the angular speed. Now the angular speed is theta divided by time. And I'll try to get this figured out. Theta is the number of radians try to think of what to be turned, moved, rotated. Oh, rotated. Number of radians rotated, and obviously time. In this case, is 1 minute. Well, here goes. In one revolution, wouldn't this fan rotate 2 pi radians? In 55 revolutions, then won't it go 55 times 2 pi, which is what, 110 pi. So that guy there is what theta is in this case. It's a total number of radians, right, that gets rotated. And so the angular speed is the total number of radians divided by the time, which in this case is kind of silly because it's just 1. And oh, the question did not say to 2 decimal places. Isn't that a clue that they want the answer as an exact value? And since they want it as an exact value, you do that. If they said, give me the answer to 2 decimal places, then I would go to my calculator and I'd go 110 times pi, and I'd have written down 345.58. And the units here would be radians per minute. So it's just bear in mind whether they want an exact value or a rounded off. Are we good with that? Now, did you notice that 28 never appears in any part of that calculation? Because if the fan was twice as big or half the size, its angular speed would be the same number. Because angular speed doesn't really take into account or care how long the radius of the thing that's turning is, right? It's still got the same angular speed. There is a second term that does care about the length of the blade, and that is called linear speed. And the linear speed of a turning object is the total distance traveled divided by time. Well, time is easy. It's 1 minute in this case. Now, what's the total distance traveled? Well, let's go back to this guy here. Remember, the radius was 28 inches, right? And 1 revolution would be 2 pi r, which would be 2 times pi times 28, which is what, 56 pi. Wouldn't that be the distance traveled when it rotated just once? Great. It would travel that far. But we had 55 revolutions. So if I want to get the total distance, I would get 55 times how far it would go in 1 revolution. And then I do my calculator and I'll do 55 times 56. And since they didn't mention any rounding off, that guy there is the linear speed. When you take that and divide it by 1, which is the same guy you started with. And the units will be inches per minute.
Yeah,
So-
how did you figure out the revolutions?
And they told us in the question that it was
Oh.
going to be 55 revolutions. I mean, you know, I'll change each time. If you think about what that is telling us about an object that moves circular, right? You know, like a child's roundabout. I don't know if they have them in America, but you know what a roundabout is, what I call a roundabout? There's these things that there's like a little lip on them. They're probably dangerous and bad now, but they existed in Scotland, where you would stand on this and you'd hold onto a little railing, because there's the little railings. And then they went round and your dad would, you know, push you and you go round in circles. Am I talking nonsense, or some of you are nodding, so you know what the heck I'm talking about, right?
Yeah, they have like
Yeah.
a turntable in the middle.
Yeah,
Yeah.
yeah.
The
So,
park itself.
right, so they do
In the US,
exist.
they're often called like merry-go-rounds or
Merry-go-rounds,
carousels.
okay. We call them roundabouts. It's good. You know the roundabout on the roads?
Yeah.
You call those
That's what I thought you
roundabouts,
were
right?
talking about at first.
Yeah. Well, we, God, no, don't let your children play on those. No, that's a bad idea. But the other things are also called roundabouts. In fact, roundabouts existed before we built roundabouts on roads. I mean, they're hundreds and hundreds of years old. Anyway, back to my story. If this was 10 feet, wouldn't you be going pretty fast? Right? Right? If somebody gave you, you know, 55 turns in a minute, you'd be going pretty fast, right? But if you moved it up to 100, wouldn't you be in one of those big carnival ones? You've seen the big carnival versions where people get stuck to the wall because they turn so fast. Now, why is that happening? Well, if you are on a really long radius, isn't your linear speed really fast? Couldn't you be going 50 mile an hour? And if it's only, you know, whatever, 10 feet, you're not going to do anywhere near as fast. Yeah, I don't know how many kids in Scotland break legs on those things. I'm surprised they still exist in America, because don't you sue everybody the minute something bad happens?
I actually don't know the last time I saw one at a park, but they were a thing when I was a kid.
So somebody probably in Kansas sued the county and got 20 million. So the county said, okay, we'll just get rid of them all, right? So there's probably one left in Arkansas that nobody has found out about. Right?
There's one in Paulsbo.
Well, while it's still there, nip over, fall off, Caitlin, and claim that you were injured by the dangerousness of the object that you fell off, right?
Yeah,
And sue them. And
sounds like a great plan.
can you get a lot of money?
I bet I could.
Yeah. Okay. Unfortunately, I've now got another joke, because I've got to tell you, because Arkansas came into my head. Do you know that the toothbrush was invented in Arkansas? Did you not know that? They found out it was invented in Arkansas because the toothbrush would have been called a teeth brush if it had been invented anywhere else.
That's
pretty
good. That's really
You
good.
can substitute the Arkansas for Belfair, and I think it would work out. So.
Now, you be nice. I'll insult whichever state I want. You can insult whichever one you want. Okay. Right, let's do one more of these revs per minute questions. And that's pretty much the end of what I'm going to be doing on this section. So just randomly picking one that I saw. In this one, it's a paddle wheel. You know, in those old steamships. And what they, as I read through it, what they're telling me is that the radius is quite a small one, right? 0.5 meter. And it rotates at 100 revs per minute. And they want you to find what's the speed of the boat. So you've got, you know, if you imagine the boats, you know, they look like that. You know the ones I'm talking about, the paddle boats, right? Paddle boat, 100 revs per minute. They want to know what the speed is, right? And they want to know the speed in meters per minute. So basically, don't I just need to find out what the total distance traveled, right, on the outside of that wheel when it does 100 revs? So it's going to be very similar to what I've done. It's going to be 100, right, 100 revolutions times one complete circle. Now, if you do one complete circle, isn't it going to be 2 pi radius? So it's going to be 100 times 2 times pi times 0.5. You couldn't make the numbers easier if you tried. It ends up being 100 pi. And so your speed is going to be your distance traveled divided by the time, which happens to be 1 minute. And so you can't get much easier than that. And so it's that guy, meters per minute. And since they didn't ask for to 2 decimal places, you realize I'm leaving the answer as an exact value. And in fact, that is the way that many things measure how fast they're going. They measure something that turns, that they have a fixed radius, right? And they measure how many times it goes round in a minute or a second or an hour, whatever the units happen to be, probably a minute. And then you can convert that. I could convert that into miles per hour, couldn't I? Or it wouldn't be miles, it'd be kilometers per hour, wouldn't it? And all I do is divide it by 1,000, which if you want to know, it's doing about 3.1 kilometers an hour, which is absolutely crawling. I mean, it is not moving at all fast, but that's what it would be. Any questions before we move on to our next section? Are we good with these ones?
I had a quick
Yes.
question.
Mhm.
This might be kind of obvious. Right after the 100, there's an X. Is that an X as in a variable or an X as in multiplication?
It's an X as a multiplication.
Okay, thank you. Sorry.
No, I want to, well, let's show you why I do that. Idiosyncrasy of being in Britain, being Scottish. If you've had me before, you know this one. Have you noticed that my decimal points don't always end up where you expect them to be? They seem to be a bit higher than usual. If I said, what was that? I hope you would say, oh, you mean 3.145. And if I said that, you might say, oh, you want me to do 3 times 145. Have you noticed that about me? Well, that's because in Britain, decimal points go there. And in America, decimal points go there. Our decimal point is in a different location. And since I've been in Britain and Scotland and educated there, it's kind of hard for me to move that decimal point, right? That's where it goes when I write it, it just automatic. Well, just for curiosity's sake, do you know that if you're French, that's 3.145? In fact, if you're Russian as well, I believe it's 3.145. Do you know they use a comma instead of a decimal point? See, you now know stuff. So if I want to do 3 times 145, do you see why I have to do an X? Because back home in Britain, that would cause an awful lot of confusion, wouldn't it? Do you want me to multiply them, or is that a decimal? That's what people in Scotland would be thinking. Actually, they wouldn't. They would say that's a decimal. They wouldn't think about it at all. So that's more than you wanted to know, lad, right? But that's why I do it. So we are moving on to our next section.
I just have one more question.
Oh, go for it.
I'm sorry. So when it's asking for speed, do you just like always assume it's linear speed first, or do you like, does it tell you angular or linear?
If it says speed, you mean linear.
Okay.
Right. If they want you to do that angular speed thing, it will use the word angular speed.
Okay.
There's not many questions that ask you if you're angular speed, so you'll know them when you see them because it'll say angular speed. In fact, when it does that one, it's normally got 2 questions. The other one then is linear speed, so it asks you for both.
And then I have one more. The total distance traveled, isn't it just revolutions times the circumference?
Yes.
Okay, making sure. All right. I'm good now.
You're good. Oh, good. That's a good answer stroke question. So no wrong with that. So we're now going to be looking at the rest. I don't know why I called it 6-1 because I think it's actually 6-2, but whatever. Maybe it's 6-1. Yeah, still 6-1. But this time we're going to do radians, degrees, and coterminal angles. Well, the good news is we've actually done an awful lot of the radians and degree questions because they are really just convert from radians to degrees or convert degrees into radians. So, right, so there's just a whole bunch of questions at getting you plenty of practice at changing radians into degrees or degrees into radians. Now, we'll not worry about the coterminal angles until tomorrow. So here we go. Suppose I want to find degrees, but you told me radians. Right. Can anybody remember the formula that if I give you, 4 radians or pi upon 2 radians, how you figure out what that is in degrees? What's the formula?
Uh, 180 times the radians divided by pi.
Okay, that works. You happy with that? Or 180 radians times pi probably sounds nicer actually. Okay. What about the other one? you tell me the degrees. I want to know how many radians it is.
Divided by 180 times pi.
When you look at those two equations together, isn't one kind of just a reverse of the two numbers? So you multiply by 180, divide by pi, or you multiply by pi and then you divide by 180. You agree they're very similar equations. In fact, if you know one, you can actually, by solving for the other missing thing, you can create the other one, right? So if I wanted to go from here to here, I would multiply both sides by pi and then divide both sides by 180, and this is what you'd get. So you got those, guys. It's really just a matter of conversions. Now, if the question says to 2 decimal places, calculator. If it doesn't, isn't your answer going to be 7/9 pi or 42 over pi, right? It's going to be exact value, right, with a pi in it probably. Right. So let's take a baby one to start the ball rolling. 66 degrees is going to get turned into radians. So 66 degrees is 66 over 180 pi. If they want the answer as an exact value, then I would do 66 divided by 180 and then hit the math button choice 1. And I would say that the answer was 11/30 pi. If they wanted this answer as, say, to 2 decimal places, then you go 66 pi divided by 180 and round off the answer to 2 decimal places. So, exact value and rounded off value. And one of the reasons I'm pushing this is it's so easy to not read the question carefully, and you put the 11/30 pi in, and WeberSign says you're wrong because it wanted, you know, the 1.15, right? Or vice versa, right? So if it doesn't mention rounding off, do that. If it does, round it off to whatever it says. I haven't done this one, but it should be pretty straightforward. I want to turn -30 degrees into radians. Okay. Well, isn't it the angle over 180 pi? Agreed. -30 goes here. Divide by 180 times pi. And that ends up being 1/6 pi, or as a decimal, 0.52.
It would be negative though, right?
Oh God, yes. Well caught. It would be negative. Now, suppose they gave you some ridiculous angle, right? It doesn't matter. Isn't it still angle divided by 180 and a pi, right? So if I was trying to do that as a decimal, which I'm sure I would, and the answer, at least to 2 decimal places, would become that one. As questions go, would you agree that's pretty much plug and chug? There's nothing to think about. You just make sure that you use the right equation and everything should come out nice. So let's go the other direction. Suppose I had pi over 10 and I want it to be converted into degrees. Then it would be radians times 180 divided by pi. And they didn't mention in this question, which by the way is question 6, that they wanted it to any accuracy. So that means it's going to be an exact value. So I'm going to cancel that pi with that pi. So what I'm really left with is 180 over 10, which is 18 degrees. You see, it came out really nice. Suppose they give us negative 11 thirds pi. Well, it'd be negative 11 thirds pi times 180 divided by pi. So those cancel. And if you do that guy times that guy, I'd probably do it in the calculator. So put a bracket around it for safety. Negative 11 thirds times 180. And the answer I get is negative 660 degrees. Comfortable with that? You could get a number like 3.5 radians. Now in this case, you would be asked to do it to, let's say, the nearest whole number. So this would be similar to question 5. So it would be 3.5 times 180 divided by pi. And that's 3.5 times 180 divided by pi. And they want the answer to the nearest whole number. So in this case, I think it would round up to 201 degrees. So if I gave you any angle in radians, are you comfortable about how you could turn it into degrees? And if you wanted an exact or a decimal, you know how to deal with that. And if I give you any angle that's in degrees, you could turn it into radians and do the same thing.